and that's why we use the reference electrode. So what we are doing, we are simply converting hydrogen ion concentration into some potential, and then this potential is being measured by with respect to some reference electrode.
Yes,
So,
sir.
so what you did, you simply converted your concentration into some potential, and you draw a calibration curve and you make your pH meter. So that correlation is very much important. That you convert one non-measurable unit into one some your measurable unit. That is the ultimate aim.
Yes, sir. But sir, there a case arises where if I want to know about the concentration of something, and that
Yeah.
particular thing is neutral in nature, if not
Mhm.
an ion, if it is neutral in nature, then how with the help of electrochemistry I can measure its concentration?
See, for example, there are mostly things are like electrochemically active species. Whenever we say electrochemistry can be done with electrochemically active species, fine. So electrochemically active means either mostly it will be ionic or it will be
Ions.
polar in nature. For example, this glucose. So what we are doing in this glucometer, where we are measuring the sugar level, we are simply measuring the uh, this glucose concentration. Okay,
Yes, sir.
so glucose is not ionic, but
Yes, sir.
but somewhere it is polar in nature. So what we do, it becomes electrochemically active. So what makes it electrochemically active? When we apply the potential in that strip, when we apply a potential difference, and then what at particular potential, this glucose breaks down or it gets oxidized. Fine. So that oxidation, we got a signature again. So that oxidation, with the help of that oxidation, some current flows. We simply measure that current. So in electrochemistry, either you should be able to convert particular molecule, it might not be ionic, convert that particular molecule in some other form by oxidizing or reducing it, or you can directly be able to convert particular molecule by using it. It might not be ionic. These are the two. Convert that particular molecule in some other form by oxidizing or reducing it, or you can directly be able to convert particular molecule. Anyone else?
Anyone? I think all are satisfied, sir.
Okay, that's a good news, sir.
So, thank you, Doctor. Thank you, sir. Anuj Awasthi, sir, Director and Co-founder of Canopy Techno Solution Private Limited, for the very nice, wonderful, and technical enabled presentation for water quality analysis. So thank you so much. Now I invite technical enabled presentation, research for water quality analysis. So thank you so much. And private. Now I invite technical enabled presentation, research for water quality analysis. So thank you so much. And private. Now I invite research Gyan Prakash Sharma. He is a research advisor in Canopy Techno Solution Private Limited. He obtained his PhD degree in chemical engineering in the year of 2019 from Indian Institute of Technology, Kanpur. He obtained his master degree in chemical engineering from Indian Institute of Technology, Roorkee in the year of 2011. He obtained his bachelor degree in biochemical engineering from HBTI, Kanpur in the year of 2009. He has published 7 research papers in international SCI journal, reputed journal. He published 4 book chapters. He delivered the talk in invited as an invited speaker in more than 10 talks. And his research experience is also in a fabrication of function of nanomaterial for electrochemical engineering storage, and fabrication of functional nanomaterial for photoelectrochemical generation of hydrogen gas. He holds a membership of Electrochemical Society USA. He also awarded he also awarded various prizes and awards like Gandhian Young Technological Innovation Award by Society for Research and Research and Initiative for Sustainable Technologies and Institutions. He awarded third prize in Prime 83 Innovation Award for project entitled Fabrication of Novel Photocatalyst via click chemistry for hydrogen production from IIT Kanpur, India in the year of 2013. He also supervised several theses of UG and PG students, more than 10 students over the past 10 years. I again heartily welcome you, Dr. Gyan Prakash Sharma, sir. Sir, you can start your presentation, sir.
Thank you very much, sir. Once again, I warm welcome everybody for the second day of the workshop. And this is my second lecture. And the previous lecture, we understood about the basics of electrochemistry and then followed by a lecture regarding the electroanalytical methods. So I hope that people have understood the basics, the fundamental, and they are now ready with the applications part. And if you have any query or any question, so you can contact me on my email ID, which I shared previously yesterday. Other thing is, if you want to ask any question related to the previous presentation, so you can ask at the end of this lecture. So without further delay, we will start the lecture. So I'll just share my screen. Okay, so I believe that the screen is visible to everyone. So today's lecture is about solar hydrogen generation, and it has immense potential. And the agenda of this lecture is to familiarize all the audience about the upcoming methods of energy conversion and utilization. This lecture will benefit all different kind of researchers who are working in renewable energies to help to understand the technologies available, what is the state of the art, and how do we proceed further. Okay, so without further delay, we will start. So this slide, I think the slide is visible to everybody. If it is so, please say yes.
Yes, sir.
Yes, sir.
Yes, sir. Okay. Okay, so on the screen, you see that there's a word chart and it shows the distribution of energy consumption in different part of the world. And you see that the different colors represent the amount of energy being utilized per person per year. In the left bottom, you see what is the tentative quantification of the colors, and from the picture, you can very well judge that the distribution of energy consumption is not same. It's very inhomogeneous distribution. For example, very advanced countries like US and UK, Australia, their power consumption is very high. But there are very poor countries like South Africa. There you see that their consumption is very less because they do not have energy for consumption purpose. In between comes is the developing countries like India, China. These are all Asian countries where the consumption of electricity is moderate consumption. Okay, so all in all, what we need is the energy. The population is growing day by day. We need more and more energy. So from where we get the energy? We have to convert the energy from the natural sources itself for our daily uses. Okay, so just realization of the fact that how much energy do we need. Okay, I just
common point of view, if you see that how much energy a person can use in a day. Let's say we are using two fans and two bulbs continuously. So it is continuously, when I say it is 24 hour if we run. Okay, that not so happen. And also it is not possible in everywhere in the world where there is very extreme cold. Their fans won't work. We need the heating system. Okay, and where there is a cozy environment, we do not need the fans at all, as well as we do not need the heaters at all. So, just for understanding and the normalization purpose, we see that if we take two fans and two bulbs as an average energy consumption per person, so what is the energy we need per person is 180 watt, and this 180 watt converts per year is 2.84 gigajoule per person year. Now, what is the total population of the world? If we see, it is 7.8 billion as per the record on the government side in 2019. Okay, for all this population, the total energy is the whatever is the energy required for 1% multiplied by 7.8 billion population. That is 0.63 terawatt of energy. From where does it energy come? So we have fossil fuels, which contributes the 85% of total energy being utilized. These fossil fuel consist of coals, oils, natural gases. So what is the advantage of the fossil fuel? That it is available in the nature. We take it, we dig it, and then we refine it and we utilize it. But what is the drawback? The drawback is when we utilize these sources of energy, we deteriorate our environment by the production of harmful gases. Other thing, by the time, since the fossil fuels are limited in nature, the fossil fuel reserves are depleting, and after some time, they all will exhaust. So after few years, we won't be able to depend on the fossil fuels. So what we need to see, we need to see some alternate source of energy is the renewable energy. Presently, the contribution of renewable energy sources is 15% for the total energy demand. This consists of the wind energy, hydropower energy, and solar energy primarily. And in all this technology, if you see, the wind energy is dominating right now uh, in context of commercialization. So, but the problem with the renewable energy is this energy is intermittent. It is not readily available at all times. For example, the wind energy is not available when the environment is very still, there is no wind blowing, and similarly, if you see, the solar energy is not available in the nights. Okay, so they are intermittent source of energy. So there's some limitation, but what we see that this is non-exhaustible source of energy. So for a longer run, if we want to depend on energy source, we have to rely on renewable energy sources, and we need to just cut our requirement from the fossil fuel. And when this corona pandemic started, everybody know that the uses of while the lockdown happened, the uses of the vehicles was depleted so much that the crude price decreases drastically. And you might have heard also that a point was there when people say that prices of crude is negative. They are giving it to you free of cost, and also they are paying you some money if you are taking the crude. So actually, this is not the thing that they are paying money. It is almost free. The duty charges were exempted at that time. Okay, so that's why after the corona, the most Gulf country, which is the big producer of the fossil fuel, the crude oil, are in not a very good situation financially. And that you can see that we cannot rely on the fossil fuels. And now we just moving to the renewable energy sources, we see that the solar energy, if we talk about what is the potential of the solar energy. Okay, So in this, you see, this Earth is always get illuminated with the solar energy, and since it revolves, the phase which is in front of the solar radiation that gets illuminated. Where there's a day, other side is the dark. There's a night. Okay. So total energy which is coming over the surface of sun is 12 lakh terawatt. Okay. So, and if you see the total surface area of Earth, which is available with us, is 1.6 into 10 power 8 kilometer square. Okay, so how many of you knows what is the radius of Earth? Tentative radius. We know that it is not completely spherical.
So 6,400 kilometers.
Yeah, approximately it is 6,400, 6,400 kilometers. Okay, so in the previous slide, for whole population utilizing two fans and two bulbs, the energy required is 0.63 terawatt. How much area of Earth is required for that? If we calculate, we'll come to the conclusion we need only 85,000 kilometer square of area. That will produce the energy that is sufficient enough for each and everybody to run a fan, run two fans and two bulbs 24 hours whole day. And what is this area? If we physically want to understand how much this area actually you can realize. So this is the graph, the map of Indian continent, where you see that 85,000 is only one fourth of the area of the Rajasthan, or in the MP, it is one third of the MP area. Okay, so now you can understand that how smaller space is required to satiate the need of everyone. Okay, so now one thing, this is just for understanding what is the amount of energy we need, and what is the potential of solar energy to satiate that need. Now, how do we harness the solar energy? So there are different technologies being developed, and what are those technologies? That solar energy we can directly convert it into the electrical energy, and that is through the solar cells. We say it the photovoltaics. This is a direct way. Okay, it utilizes the semiconductor material, and there the semiconductor material produces electron and hole, and those are being separated far enough with the energy differences of the electrons, so that we can utilize when we connect it through the external load. Okay, so this is one way of the solar energy harness. What is the other way? We can utilize the solar energy in a photoelectrochemical system, where we break the water molecule and convert into the hydrogen. Hydrogen is a fuel. Yesterday we discussed that it is a potential fuel of the future. And in this process, the solar energy again harness the energy through semiconductor material and do the electrochemical reactions on the water molecule for the production of hydrogen. Okay, so these are two ways. And also, if you see that these are two legs, we discuss one and one. We can also interconvert the electricity which is generated through the solar energy to the fuel by providing the electricity generated directly to the water molecule to split the water. Okay, so this is the third thing. Fourth thing is this hydrogen and oxygen. They can recombine together to generate the electricity. This is a reversible reaction, which is known as a fuel cell. Hydrogen and oxygen, they combine together in a fuel cell and produces the electricity. And of course, the byproduct is the water molecule again. So the importance here of the solar energy comes is it has immense potential, and we are developing the technology for the utilization of the solar energy into useful form. Okay. Now, if we directly convert to the electricity in solar energy, what is the drawback? The drawback comes here that we have additional device to store the electricity. We know it as battery. Okay. So the drawback comes here that it is not instantaneously charged. It takes some time. We cannot just store the electricity in a battery within a fraction of second. Okay, so we have to rely on other system where the energy can be stored and it is readily available. And that's why we talk about the photoelectrolysis of water molecule for the production of hydrogen, which is a chemical fuel. Okay, which is readily available. You store it, and whenever you require, you can use. Okay, so we'll focus on what is photoelectrolysis. So this is photoelectrolysis setup. I'll show the schematic. How does the system work? So basically, it has the water where the two electrodes are dipped. So at least of these two electrodes should be semiconductor material. Okay, it may be either one or it may both of the semiconductor material so that it can harness the solar energy. So once we radiate the solar energy on it, let's say this material is the semiconductor material or solar active material. So that causes the generation of electron and hole. Okay, with the generation, they separate from each other, and after the separation, the hole reaches at the surface where there is interface of liquid and solid is present and participate for the oxidation of the water molecule, and that result into the formation of oxygen as well as four protons. Okay, so these four protons move to the other electrode. Simultaneously, the electron generated on the semiconductor material that also move through the external circuit to other electrode. They meet at the interface and the other electrochemical reaction happens, and with this electrochemical reaction, the combination of proton with electron that results into the formation of hydrogen. Okay, so here if you see this reaction with the help of the hole happens to be oxidation reaction. So therefore it is an anode. Since this material is also a photoactive material, so that's why we say this material as photoanode. Similarly, since the reduction happens here, so this is a cathode material, and if this is also solar active or a semiconductor material, then we'll say it as a photocathode. Okay, so now we know what is the photocathode and what is the photoanode material. Okay, now we will move a little deeper into the fundamentals of this schematic, how the things happen, how this reaction happen, what are the different conditions. Okay, so before understanding the different condition, we will focus on the semiconductor material. Okay, so what is the semiconductor material? Everybody knows it has some band gap. So I'll tell you about what is the origin of the band gap, from where the band gap comes. Okay, so when we see that the band gap comes, we have studied the molecular orbital theory. So development of band gaps comes from the molecular orbital theory. For example, if we have any material, let's say we have silicon. Okay, silicon has some electron in its outer shell, and there are NPDF shells are there, SPDF shells are there, and again 1s, 2s, 2p6. There's a electronic configuration. Okay, so silicon interacts with another silicon. Silicon interacts with another silicon, another silicon, another silicon. So the interaction happens by the interaction of the electrons in the orbitals of silicon. How does this electronic interaction happen? That happens through the molecular orbital theory. which says that when the electron interacts, they bind together, and there are two different kind of orbitals uh, 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 generates. One is the bonding orbitals, and one is anti-bonding orbital. So bonding orbitals are having the energy is lesser because they are bonding, and they are the filled orbitals. Anti-bonding orbitals are generally unfilled orbitals, and their energy is that's why lesser. So there's a when we have different so many silicon atoms together, it makes a material which we can see from our naked eyes. Okay, so there are lot of electrons are involved there, and when lot of electrons are involved in from the molecular orbital theory, there are lot of bonding orbitals, there are lot of anti-bonding orbitals, and we have the energy levels of the bonding orbital level in a close proximity. So all these bonding orbital energy level in the close proximity together makes a band. This is not something kind of rubber band. It is kind of the close proximity of different energy levels. So when we talk about the bonding orbital, it makes a band which has the filled states or filled orbitals with the electron. That is known as the valence band, and the energy of the valence band is lesser. Okay. Other thing is antibonding orbital. Antibonding orbitals are the unfilled states of the electron, which is having high energy, and that is known as the conduction band. Okay, so there are different energies states here, different energy states here. They are all combined together to form a band. Okay, now what is the highest energy level? This is known as the valence band edge. Okay. Similarly, in the conduction band, the lowest energy level is known as the conduction band edge. So these are some definitions I just mentioned you. Now, what happens and different kind of material? What are this energy levels? What is the difference of this energy levels defines whether this is a metal, it's a semiconductor, or an insulator material. So what happens in a metal? These valence band and conduction band overlap together. When this overlap happens, means that the valence band electron which are in the bound state, they can move to the conduction band easily. There is no energy barrier for it, and they are in the conduction band. These are unfilled state, so they can move there freely. So that's why what happens that metals are having the free electrons and they are conductive in nature because the valence band electron can move to the conduction band and they can move freely. Other comes is the semiconductor. In the semiconductors, the gap between the conduction band and valence band varies from 0 to 4 electron volt. Okay, so when this is the case, it needs a small energy perturbation for an electron in the valence band to move to the conduction band. For example, if we shine the light on the, let's say, silicon is a semiconductor material of band gap of 1.1 electron volt. There if we shine light, so the material takes the energy, and the energy energize the electron so that it can move from the valence band orbital to the conduction band orbital, and now it becomes free, it can move. So previously in the dark condition, which the material was working as an insulating material, but when we shine the light, because of the electron excitement and then movement, it becomes a conductor material. So that's why we say it's a semiconductor material. And the next category is the insulator material, where the gap is so large that even if we give a very high amount of energy, the electron that cannot reach to the valence band level. Okay, so there is no free electron. If there is no free electron, there is no conductivity in the system. So that's why it is insulator. So I think this concept should be clear to everyone. Now we'll move to what is the fundamental requirement of a PEC setup. Okay, So we saw in the schematic that the reaction what were happening on the cathode and anode. The cathode, of course, it is a reduction. We discussed in the previous lecture that on the cathode reduction happens. So protons in association with electron convert to the hydrogen. And what happens at the anode? Anode is the oxidation. So water molecules that converts to the oxygen and proton. Okay, so these are the reaction which happens. Now if you see the reduction potential of these reactions, so for the cathode it is 0 volt versus normal hydrogen electron, and for anode where the oxygen evolution happens, it is 1.23 volt versus normal hydrogen electron. Okay, so for hydrogen evolution this happens at 0 volt versus energy. For oxygen evolution, it happens as 1.23 volt of energy. So when combine these reactions together, we will get the water molecule splitting into hydrogen and oxygen. Okay, you can balance the stoichiometry because there is 4 electron, 2 electron. So how many number of what is the coefficient you need to multiply? You can do it. Okay. So from here, when you calculate the energy requirement, will come 1.23 minus 0, and that is 1.23 volt. So this is the thermodynamic means theoretically required energy for splitting of water molecules into hydrogen and oxygen. Okay. Now, if we have a semiconductor material, so how does this conditions are fulfilled? Okay. We have here is energy scale. This vertical line is a energy scale where the voltage energy scale is increasing in the negative direction, and we discussed in the previous lecture that if voltage is decreasing, the electronic energy is increasing, and if voltage is increasing, the electronic energy is decreasing. So if voltage is increasing in this direction, the electronic energy is increasing in this direction. So we will talk about the electronic energy increment. Okay. We saw that in the previous slide, the electronic energy levels of conduction bands are higher than the valence band. Okay, this is one thing. Other thing, on this energy scale, if we find out what is the potential at which the reduction reaction happen, that happens at the 0 versus energy. Okay, and if we have a semiconductor, we need electron from the semiconductor material that only comes from the conduction band. So what is the condition? That the electron from the conduction band will participate in this reaction to produce hydrogen. That is, the electronic energy should be higher than the electronic energy level of the hydrogen reduction potential. Okay, so that is what written here, that the electronic energy level means the conduction band edge should be higher than the hydrogen evolution reaction half cell potential. Lesser means on a voltage scale I have written the lesser, however in the electronic scale it is greater. Okay, similar fashion, if you see that when the oxygen evolution happens on energy scale, it is at 1.23 volt, and the the hole which participate, the electronic energy should be the electronic energy of this oxygen evolution reaction should be higher, so that a a hole can come and participate in this reaction. Okay, or alternately, you can say that electron can move from oxygen evolution reaction to the valence band. Okay, so these are two conditions, that hydrogen, for in case of hydrogen evolution, the conduction band edge should be more above, and for the oxygen evolution reaction, valence band H should be below the level of oxygen evolution reaction. Okay, so till now this is clear. Okay, we know that the difference of hydrogen and oxygen evolution reaction is 1.23 volt. And that's why from our discussion, it is clear that the band gap of a semiconductor material should be more than 1.23 electron volt. Okay. So the material which are having, this is the primary criteria, which are having the band gap more than 1.23 electron volt, they can participate for water splitting. Sometimes you will see that a material is not having 1.23 electron volt. Okay, it may have 1 electron volt. Okay, so it is less than the thermodynamic potential of water splitting. So this cannot split the water molecule altogether. But what it can do, it can either participate in hydrogen evolution reaction or it can participate in oxygen evolution reaction, depending upon what is the position of conduction or the valence band. For example, if the position of conduction band of a material which is like that, the similar, but since it is having a band gap of 1 volt, so valence band would be somewhere here, let's say. In that case, if you see, this conduction band electron is can participate for hydrogen evolution. This can evolve the hydrogen, but this valence band hole has not sufficient energy which can participate for oxygen evolution reaction. So such kind of material are specifically focused for hydrogen evolution reaction, and vice versa. If the valence band is present here and conduction band is somewhere here for a lesser band gap material, let's say this. So the oxygen evolution reaction is favorable, but the hydrogen evolution reaction is not favorable. So those are OER evolution kind of semiconductors. Next come when we generate the electron and hole by the excitation of light. So electron and holes are merely the energy. It's a energy distribution of the energy. So it is a polarized form of energy. But if you see in a space, they are all together there itself. So what we need to separate this energy entity from each other so that they can be utilized for our specific purpose. Otherwise, what will happen? They will be combined together, and the heat energy will produce. Okay, so that's why we say that it should facilitate the creation of charges and then they separate it also. And for the separation, uh, uh, what happens after the separation, they should move to the surface of interest where it can participate for hydrogen evolution or the oxygen evolution reaction. Okay, now these are the conditions how a system can respond to a particular material. Okay, if we come to the characterization, how do we characterize such material in from the experimental point of view? First, what we need to know that if we have some material, what is the band gap? Okay, so if it is having a band gap less than 4 volt, 4 electron volt, then it is semiconductor material. We can utilize it for photoelectrochemical water splitting reaction. Okay, so first we find out what is the band gap. From that, for that, what we do UV visible spectroscopy analysis. The data, what we get from there, we do some calculation. Basically, there's a plot which is known as Kubelka-Monk plot, and from there we find out what is the band gap of the material. Now we have a band gap. Let's say we got a band gap of 2 electron volt. Okay, now we know that band gap is 2 electron volt. That is well suited for the water splitting reaction. But this reaction will happen only when the band edges, the conduction band edge and valence band edges are at the appropriate position. So we need to find out the band edge position. Okay, for that we used to do ultraviolet photoelectron spectroscopy, and from there we find out what is the position of valence band. Okay, once we have the valence band position, and from there at 2 electron volt up, we will be having conduction band position. Okay, now we have the positions, we have the difference. We need to check whether these positions are suitable for hydrogen and oxygen evolution reaction or not. If it is so, we will proceed further, and we will do electrochemical characterizations. And we see in the second lecture of previous day that there are different electrochemical characterization technique. Here I show is a simple cyclic voltammogram technique. How do we perform it? Okay, we connect it. We connect the material through the whole circuit, and then what we do? We do the cyclic voltammetry. Okay, and we find out the OCP, the open circuit potential. Okay, in the dark condition and light condition. If in the dark condition and light condition the OCP changes, it is a clear indication that the material is photoactive. This is the first proof that we can proceed further with this material. Now we do some quantitative measurement. For that, we do the cyclic voltammetry. Here you see that the y-axis of this curve is the J. This is the current density, and x-axis is the potential we apply with respect to a reversible hydrogen electrode. Okay, so we here are seeing the forward scan only. First, we do the study in the dark condition. We do not apply any solar energy. So the black dash line, this line, you see, this is the response of the material for electrochemical reaction for water splitting. And here we are interested in the oxygen evolution reaction. That's why we are moving in the positive direction. You see that here the current is 0 till approximately 1.7 volt, and then current rises. Okay, so we saw that 1.23 is the thermodynamic potential of water splitting, but in real condition the potential is more than 1.23 because of some over potential associated with the experimental conditions. Okay, so what is the over potential here? Is the approximately 1.7 minus 1.23. Okay, so there's a way to calculate also the over potential, that we need to draw a slope here, we need to draw a slope here. What are these two zones? This is non-Faradic zone and this is Faradic zone. Okay, so when we draw a slope where it cuts together, that is the onset potential. Okay, so now we see that the oxygen evolution happens at 1.7 volt. This is the dark condition. Okay, now we repeat the same technique, and now the difference is that we apply solar energy also along with the potential scan. So how the curve looks like? So if you see this black solid line, I'll highlight it because it is not visible. It is like this. Okay, so now you see that the oxygen evolution or the onset is very earlier than 1.7 volt, and this is because now the solar energy is also participating for the oxygen evolution reaction, and you see that the current is increasing where previously it was 0 in the dark condition. And so at any point, what is the difference of the dark and light? This is known as the photo current, or in this plot, since we are plotting the current density, so this would be the photo current density. Okay, so now we know that with the potential how the photo current density is going to change. Okay, Now we know that when we apply the cyclic voltammetry technique in the dark and light, we can measure the photocurrent or photocurrent density. And then we do a chopped cyclic voltammetry. The chopped cyclic voltammetry, what it is like we are applying solar energy, but at a constant interval. For example, just on off, on off, on off, on off. For let's say 1 second off, 1 second on, 1 second off, 1 second on. Then what happens? The curve will look like when there's a dark, so it will remain. As soon as I turn the solar light, it goes up and then move like this. Okay, now I turn off the light, so it follows the path of dark, and then again I turn on the light, so again it takes like this. Okay, now I turn off, I turn on, I turn off, I turn on. That's how it proceeds. So this kind of signal what we get, this says about the response of material towards the solar light, how quickly it responds to the solar light, that we find out from the chopped IV curve. Okay, now we also know, we also discussed that we can find out the onset of the photocurrent, that the onset is when the light is illuminated would be here. Okay, so in the same manner, how do we calculate it here in the dark condition? We can calculate for the photo condition. Okay, now these are the quantitative measurements. There are certain resistances, certain capacitance, those all will be involved in the system. So we do the electrochemical impedance spectroscopy to find out how the capacitance change happens, how the resistance variation happens with the application of photon energy. After that, we quantify this thing with the efficiency of the material. Of course, the end goal of anything is to find out the highest efficiency material or highest efficiency device or a system for the application. So we measure the efficiency, and specifically what we measure is the solar to hydrogen efficiency. So there are two ways to measure the solar hydrogen efficiency. One way is what is the current, the photocurrent being produced. Through that we can calculate. Okay, so that photocurrent we can measure through our electrochemical workstation or an emitter. Other way is what is the hydrogen is getting produced. We collect it and we measure it, and then we calculate the STH efficiency. So there's a certain formula for it, and that's with that formula we can calculate. So we will see what is that formula in the upcoming slide. Now, after all this being done, we know that efficiency is very good. It responds to the solar light very well. It is having very nice difference in the dark current and the light current. And now we test the stability of the material. For that, we run this material at a constant potential for a very long time. So, and we measure the current produced out of the system. Okay, for example, in this system, let's say we are getting uh, zero point 0.5 milliampere per centimeter square current density at 1.5 volt. So we do the chronoamperometry. In the chronoamperometry, we set 1.5 volt, and then we see that for a run, how the variation of the current density happen. So for some time it will remain constant, and when the material degrades, the current density decreases. Okay, so if decreases and then becomes zero, so material destabilizes. So that's how we check the stability of the material. Okay, so these are a protocol for checking material in experimental point of view. Okay, now what is the benchmarking in the PC technology? In the PC technology, The material, which is semiconductor material, the band gap of the material should be at least 1.6 electron volt. 1.6 electron volt is because 1.23 is thermodynamic potential plus additional over potential for the real experiments. And ideally, we generally see that 1.6 electron volt is sufficient to break a water molecule into hydrogen and oxygen. The material, the semiconductor material, should have strong absorption of solar irradiation. It should not be like if we light sunshine, then it is reflecting or transmitting. It should absorb more and more solar spectrum so that it can be harnessed for the chemical energy conversion. Once it absorbs, the material should have high electron mobility as well as high hole mobility, or we can say the high charge mobility, so that with the generation of electron and hole, they move inside the crystal matrix of the material far apart so that they do not recombine back. And then after when they move to the two different sites, they participate for the redox reaction of water splitting. These are the condition for the semiconductor material. And other than that, what is the condition is when we take the water in the system, it is not a pure water because pure water is ionically non-conductive. We make it ionically conductive by varying the pH, either by adding acid solution in it or basic solution in it. So the material should be stable enough. The electrode should be stable enough in the electrolyte also, and also the it should have good catalytic activity for hydrogen and oxygen evolution reaction so that the over potential can be even lessened. And last but not the least, it should be cheaply available so that it can be in the reach of common people. This to track all the different research which is going on, and what's available in the market and what is our desired output of the research. There is a society, National Renewable Energy Lab (NREL), which gave the guidelines for a material to be commercialized if it shows a conversion efficiency of 10% at least, with a photocurrent density of 10 to 15 milliampere per centimeter square for with a stable operation for more than 2000 hours, and of course it should be economically feasible. Okay, so these are some standard requirement, only then the commercialization can happen. Okay, now what I talked about the efficiency. So in the efficiency, I discussed that the solar to hydrogen conversion efficiency. So this is the formula for a whole device. If we have whole device which is converting water molecule to hydrogen and oxygen together, we should find out what is the stage efficiency. And for the application purpose, whenever we talk anything, we always talk about a device. So that is a practical thing, and that is directly being utilized as a product. So there's always a competition between different firms that which company's product is better. So that depends upon the solar to hydrogen conversion efficiency, and that's why it is a benchmark. Okay, so this is a kind of material which is converting solar to hydrogen as well as oxygen. The whole, the water, complete conversion of water into hydrogen and oxygen. Okay, but for the material which are only capable of hydrogen evolution or capable of oxygen evolution, so we do the specific study of the material, and for that we do diagnostic efficiencies measurement. In that thing, what we measure that at which photon wavelength the system is responding, and how the system is responding. And for that, we calculate the incident photon to current efficiency. And this is the formula. And this is merely a diagnostic efficiency. This is not a correct efficiency. I would like to mention it. Other thing, that if a photon is incident on a material, okay, there is a probability that it not get absorbed. So in the previous, the incident photon is not a correct measurement of efficiency, because we are talking about the incident photon. It may or may not be absorbed by the material. So to make it more correct, there is another efficiency introduced, is the absorbed photon to current efficiency. So this is the amount of the photon that is absorbed, and that is converted to the hydrogen or oxygen. Okay, so this is the formula for absorbed photon to current efficiency. Okay, so these are a few efficiencies related to a system when we sunshine a light. Okay, now uh, uh, if you see in this graph, that in this portion, we are not only sunshining the light, also we are providing the electric potential. In such a system, what happens? That we are be providing the electric potential as well. In that system, the efficiency which we need to calculate is the applied bias photon to current conversion efficiency, ABPE. This is one way of showing the efficiency of the system, that how the system is responding not only for the solar irradiation, uh, also what amount of electrical energy we are providing. And there's other group which also gave another efficiency, intrinsic solar to chemical conversion efficiency. That is that when we shine the light along with the electric energy, so they can be separately calculated together. For example, in the dark, what is the efficiency, and in the light only, what is the efficiency. And when we multiply these efficiency together, we will get the total efficiency of the system, that is ISTC, intrinsic solar to chemical conversion efficiencies. So that's how there are different efficiencies are being reported in the literature. And now we come so to what are the different materials which are being utilized. And there are some oxidized semiconductor materials. You might have heard about the TiO2. You have heard about the tin oxide, iron oxide, bismuth vanadate kind of material. There are some non-oxide semiconductor materials also. So, though these materials are semiconductor material, but there is a limitation associated from commercialization point of view. What is that limitation? That either the material is having very high band gap, for example, the TiO2, it is having 3.2 electron volt. If it is having so high electron band gap, it absorbs only a fraction of solar spectrum, and that's why the whole solar energy is not being utilized. And some which are very good, I mean, very appropriate band gap, those materials are not very stable material. And that's why the technology is not successful in a commercialization point of view. So from here, what we are targeting in the commercialization point of view, that solar assisted water splitting. In that we take the solar energy, convert it into the electrical energy, and with the help of electrical energy, we split the water molecule. So lot of research has been done in this direction. So I'll show a few of the state of the arts of such kind of system. So this is first system I'll show. Here, this report was published way back early in 2011 in the Science by Professor Nocera. So what he did, he took a three-junction amorphous silicon. It's a semiconductor material. So when you or it's a solar cell. Okay, so it's commercially available in the market. And when you sunshine the light, it produces a voltage around 3 volt. So what he did, he deposited oxygen evolution catalyst on one surface, and he connected the other surface of the solar cell to another electrode where the hydrogen evolution catalyst is deposited. Now, when you sunshine the light over it, it causes the generation of electron and hole. The hole moves towards the direction of the surface of uh, exposed surface of this solar cell, and electron move to the other direction from the to the current collector, and from the current collector it moves to the other electrode where there is the hydrogen evolution takes place. So here the oxygen evolution happens at the solar cell surface itself, and the hydrogen evolution happens at the other electrode. Okay, so now what is the take home from this thing is that we can develop such a system where that there's a solar photovoltaic which is having potential more than 1.23 volt. For example, in this case, it is 3 volt, and that energy, electrical energy, being utilized by the help of oxygen evolution catalyst and hydrogen evolution catalyst for the generation of hydrogen and oxygen. So here in this system, he calculated the solar to hydrogen conversion efficiency, and that is 4.7%. Okay. He also proposed another variation, another configuration of the same system where there is no wire connected. It's a wireless mode that he directly deposited the oxygen evolution catalyst at the back surface of the current collector. Now, you can see, and it's a general intuition that since we have removed the external wire, okay, and so now the distances are lesser, then even if you see the efficiency, the STH efficiency, it is lesser than the previous case. Why is it so? This happens because in the previous case, if you see, this is not only about the electron movement, but also about the proton movement or the ion movement from one electrode to another electrode. In this case, the proton which is getting generated, it has to move and to the other electrode, which is in a very close proximity. There's a very less diffusional resistances over here. However, in this case, the proton has to move all the way to the other direction. There are very high diffusional resistances. That's why the STH efficiency is very less. Okay, so it is a practically achieved cell, and he showed a video also how the cell works. So here I'll show the video. This is the solar cell over which the materials are deposited on both sides, and when the light sunshine over the surface, that causes the oxidation of the water molecule for oxygen generation, and reduction on the other surface for hydrogen generation. This surface which is exposed is actually this surface which is exposed here. Okay, now you can see this is oxygen evolution catalyst. It's a magenta color catalyst, and this is cobalt phosphate catalyst. Okay, on the other side, you will also see the bubbles are being generated. So this is the other side. This is the hydrogen evolution is happening at the other surface. Okay, so now this system is how the practically being achieved. So it's simple. You take this strip, dip in water, and then light the sunshine, and it will start generating the hydrogen and oxygen. Now you just separate the hydrogen and oxygen, store it, and that's now you can use it whenever you require. In a similar fashion, in the previous case, what we see that uh, this device is made up of silicon solar cell and the oxygen and hydrogen evolution catalyst. So the efficiency of the device not only depend upon the hydrogen and oxygen evolution efficiencies, but also depend upon the efficiency of the solar cell. So if we use a high efficient solar cell, then our the solar to hydrogen efficiency will improve. Okay, just keeping this point of view in mind, the research has moved further. Instead of utilizing the silicon solar cell, people have utilized the perovskite solar cell. Perovskite solar cell is very important solar cell with respect to the contemporary research. And what they did, they took a perovskite solar cell where the efficiencies are very high, and electronically contacted to the electrode for hydrogen evolution reaction and oxygen evolution reaction, and that's how the system is practically achieved. So here you can see that in this picture, the two solar cells are kept outside, and the two electrodes, the hydrogen evolution electrode and oxygen evolution electrodes, are dipped inside the electrolyte, and you can see how the oxygen and hydrogen evolution is taking place. So here the hydrogen evolution is visible clearly. However, the oxygen evolution, if you see, it is somewhere here. Very small bubbles you can see it is generating here. So that's how. Uh, but why they did it so that they kept solar cell outside and not inside like in the previous case? Because for the perovskite solar cell, there's an issue of stability. Okay. However, with the advancement of research, the electrodes are being produced in a fashion so that the hydrogen or oxygen evolution material is directly deposited on the solar cell and that completely dipped inside it. For example, in this case, so the electrode is prepared like it's a conductive electrode over which a perovskite solar cell is there, over which oxygen evolution or a hydrogen evolution catalyst is there, and that's how it's being utilized for the solar energy conversion into hydrogen or oxygen evolution reaction. Okay, so in the previous slide, what we saw that the perovskite material, which are being utilized because of their high efficiencies. So this has immense potential for application into the photoelectrochemical system. So we just give a little glimpse on what is the perovskite material, and okay. I'll just see the time because it was delayed yesterday. I want to be on time, so it's already I think 1:30. So I'll just skip this portion so that we won't be delayed further, and we'll come to. I'll just give a small claim that the perovskites are kind of material which take a structure in this certain fashion. The atoms are arranged and they have the empirical formula of AMX3, where A is an organic cation, M is an inorganic metal cation, and X is a halide ion. And they arrange in such a fashion that if you see their geometry on a cube, you find that M lies at the center of the cube, X or the halide lies at the center of the face of the cube, all the faces, and A light at the corner positions. Okay, so if this is the geometry, then with this geometry, if a material exists, then we say it is a perovskite material. Okay, so this material is specifically when A is CH3 NH3 I, and M is lead ion, and X is iodide. So it takes the CH3NH3I, CH3NH3I, PB, CH3NH3, PbI3. Okay, so here, okay, CH3NH3 only, not CH3NH3 plus. Okay, so this is the CH3NH3I PbI3. is the molecule which is one is largely explored in solar cells because of its high efficiency. Okay, so that is the thing I wanted to tell here, that this material has an immense potential for uh, uh, solar to electrical, solar to chemical conversion. So I'll try to skip a few slides and then I'll come to the potential of perovskite solar cell. This is a graph. It should not be very clearly visible to everybody. So I'll focus on a specific point here. The x-axis shows the year in which the research is progressed, and y-axis shows the efficiency of the development of solar cell. So here, if you see that this curve, uh, this curve, okay. Here you see that the research of the solar cell, which was started, actually it is started in 2009. That data is not in this plot, and they have shown the data after 2014. So how quickly the efficiencies are being increased and the advancement in the research happens. And now till 2019, we have approximately 23% efficiency of the solar cell. Okay, so this is the potential of this solar cell for photovoltaic application. And not only for the photovoltaic, if we extend this research in the dimension of photoelectrochemical water splitting, it has immense potential. Okay, so I will skip these slides. These are some stability issue of the material, how to overcome the stabilities, and there are certain methods of fabrication of the films and associated challenges. Okay, so with this, what I would like to end the talk is somewhere that what is the scope of research. If we do in the field, obviously government is focusing more and more on the renewable energy sources. Okay, and now less relying on the non-renewable sources or depending upon the crude oil imported from other countries. Okay, so now the what is the recent target of the government with the renewable energy, that they want to produce at least 175 gigawatt by 2022. Okay, this is the target, and this target was decided in 2014 and will be ending in 2022. By the time it is in progress, then a lot of renewable industries are coming into picture. For example, Adani Green, they are taking care of renewable energy production, and the Tata Power, these are also coming into picture. So the commercialization is occurring in this direction. So we see that if we do the research in this direction, it has immense potential for commercialization of the research. Okay, government is also targeting 34 solar parks in different 21 states, so that the solar energy can be utilized directly. Not only this, for the 10 years, whatever the solar projects are going on, they would be out of the tax coverage. And so that if somebody is doing research, he does not bother about the extra cost which has to pay to the government for his research work. And then government has also tied up with different countries for the advancement in the material research, advancement in the technology. Okay, and then you might have seen that if you purchase a solar LED bulb, so it is very cheaper if you purchase from a government specialized shops from there, because government is not imposing any taxes on that. So this is the tax exemption of the end product for just increase the uses of the renewable energy products. Okay, and that is the subsidy provided by the government on all the solar products, and that is approximately 30% subsidy. Not only the government is doing, favorables in the direction of renewable energy, but also the government is doing unfavorable in the direction of non-renewable sources. So what government is doing that it has imposed double carbon taxes. So the person who is utilizing petrol or diesel vehicle, he has to give more and more road tax in comparison to the person who is using a vehicle, the electric vehicle, which for 1 year or 2 year, he is not no need to pay the road tax to the government. Okay, so that kind of subsidies government is providing so that this research can fulfill. So what we saw, I would like to conclude this session that in the presentation, what we saw that we realize what is the capacity of solar energy, whether it is available, able to fulfill our requirement or not. Then we understood the photoelectrochemical cell working, its principle, and we understood how do we characterize a photoelectrochemical cell. Further, how do we compare on the basis of solar to hydrogen efficiencies? And this portion I skipped, but I'll tell that solar inorganic uh, organic halide perovskite. This has immense future for solar hydrogen generation. Okay, and then we move to the one thing more related to the perovskite material, that there are certain limitation of this material. So there we have an edge of research. What is that? One is the stability of the material. Other thing, it contains a toxic component, lead. So if we find a competitive efficient solar cell which is higher stable as well as doesn't contain any toxic component in it, then it is very favorable for commercialization, commercial application. And then government is also supporting for researcher and businessman. So all in all, if I want to conclude in a line or two, I would say that still the photoelectrochemical water splitting is a nascent technology. So still it is in developing phase. It is not being commercialized. If somebody want to just become a part of this research, so it has immense dimensions for the research. He can think of the development of the material. He can think of the development of the device itself, or he can think of the development of the modification of the electrolyte for the device. So there are different part still we has not been covered in the research. So that's where we should. This is my message that in this direction, if we see that we can work, so we can contribute to our society, we can contribute to the world in a better way. So with that, I would like to end this presentation. And now, if you have any question or query, you please ask.
Hello, Sharma sir.
Yes.
Can we move to the first slide when the electrodes are there? Two electrode you are telling.
Okay. Just.
When you are telling photocathode and photoanode, that one.
Okay. Okay. Yeah. Just wait.
Hmm.
Okay. Is this visible?
Not yet, sir.
Okay. Not shared or what?
Okay, I ask the question, sir. Here, both the electrodes are of same material or for different material?
Okay. So this may be of the same material. This may be of the different material. For example, that how is it governed? Whether it is same material or different material, I'll come to this slide. Okay. So if a material is capable of producing hydrogen as well as oxygen both, likewise shown in the configuration, then we can use the same material on the anode as well as the cathode. on the one side, let's say the anode, it can produce oxygen, or on the other side, it will produce hydrogen. Now, if it is not so, like I discussed one case that band gap, the valence band is in this position. In that case, this material is not favorable for oxygen evolution reaction. In that case, this material is only being utilized for the hydrogen evolution reaction, and on the other side, we have to use the other material. So, is it clear to you?
Okay, okay, I got it. Then when we use the same material, we will not able to designate as cathode and anode. Anyone can be cathode, anyone can be anode.
The designation or the definition of anode and cathode is like where the reduction is happening.
Hmm.
Here only it acts as cathode. Okay, so we need to check where the reduction is happening, where the hydrogen is being produced. There, we will say that this is cathode and the other one is the anode.
Yes, but what do you see that if the same material is there, then in any of the electrodes, it will produce hydrogen, and any of the electrode, it can produce oxygen too.
Okay,
So,
okay, okay. I understood.
uh,
It's a symmetrical system. Okay. Yeah, it
yes,
will become a symmetrical system, then it won't work. So we need to make a system like when it is a symmetrical system, the electron and holes being produced, but they cannot move in either of the
yes, yes,
electrodes
yes.
because they do not have any energy gradient. So we need to give some energy gradient. So that energy gradient we give with the help of external energy source. Let's say in this system. Okay, these are same material. The
Yes.
electron and holes are being generated in both material, but they do not know where to move. Let's
Hmm.
say we give a positive potential, slight positive potential, so that now the system knows where electron has to move, where the hole has to move. Now they have moved. Let's say here all the holes are moved, here all the electrons are moved. So now this will work as cathode, and this will work as anode.
Yes, yes, yes. Thank you, thank you. I got it.
Yes. Yeah, so if you have query, some other questions, you may ask please. Not only with this lecture, with the previous lecture also, if you have some query, you can ask. Okay, so if
Question
not
for
so,
last questions. I think they understand very well. So there is no question.
yeah, because this is lunchtime also, so they would be hungry.
Maybe. Thank you very much, Dr. Gyanpi Sharma sir, for very explanation of need of energy and ways of harness solar energy. Thank you, sir.
Thank you very much. Mm.
And thank you, Mr. Anuj Awasthi sir, for very explanation of electrochemical instrumentation and role in water quality analysis and pollution control. Thank you, sir. And so now we come to the end of today's session. Hope you are learning and enjoying the session. So tomorrow we will meet again for the third and the last day of this workshop on 11:30 a.m. through Google Meet with the same link. So tomorrow we will learn about electrochemical water splitting and electroplating of copper on steel substrate through experimental demonstration. So thank you. Have a nice
Yeah,
day.
so I just want to mention that the tomorrow session is going to be the important session because we are going to demonstrate the experimentally how the things look like. Okay, right now till the time we discuss that this happens, that happened on the papers itself, but in the practical, how it is possible that we are going to do. So I urge everybody to be present on time and attend both of the experiment.
Thank you. Thank you, sir. I wish you all the best. Thank you, sir. And thank you all.
Okay, thank you, thank you.